Swayam Prabha. Digital India. Educated India.
Hello friends, so welcome to the course Introduction to Sampling Theory, and you can recall that in the earlier lecture we started a discussion on the double sampling, and we had understood the concept, how are we going to compute the expectation, variances, etc. And then we replace the value of population mean of auxiliary variable capital X bar by its estimate that was obtained in the first phase of the sampling, when we have taken the sample of size n prime from a population of size n prime, and we had estimated the population mean of the auxiliary variable capital X bar as X bar prime. So, we replaced that X bar prime and we had obtained the estimator, and then we wanted to obtain the approximate bias and MSE, etc. So, in order to find out the approximate estimation error, we had defined different types of epsilons, and we had obtained there different types of expectations. Now, you know that why are we trying to find out these expectations beforehand, because you know that that it is not it is, I will say, difficult to obtain the exact expectation of this ratio estimator under the double sampling. So, we are going to find out the approximate bias and MSE up to certain order of approximation, as we have done in the case of ratio method of estimation. So, the same technique is going to be used here, and there also we had first found all those expectation, and then we had substituted them as and when needed, right. So, now in this lecture we are going to find out the estimation error, and then we are going to find out the bias and mean squared error of the ratio estimator under the double sampling, right. So, we begin our lecture here, and in case if you want to download the slides of this lecture, you can go to my home page, and from there you can download the slides in the PDF format, and the address of my home page where I have uploaded these slides, it is home.iitkk.ac.in/tilde/shalab/sp. And in case if you are facing any problem in coming to this address from here, then you can also scan this QR code, and this QR code will bring you directly to this address. And in order to scan this QR code, you can take the help of any free application available in the phones. And still, if you are facing any problem, then I would suggest you that you please go to any search engine on the internet and type my name, type my institution name, and you will hopefully find my home page, and from there you can download the slides. Okay, so just for a quick review of what we have done in the last lecture, we had assumed that the population mean capital X bar is not known to us, and we are going to use the double sampling technique. So, for that what we did, we took a large initial sample of size n prime, and we estimated capital X bar from here, right. And since we are going to use the simple random sampling to draw the sample of size n prime from the population of size capital N, so the sample mean of this observation can be used, which is obtained here like this, and this arithmetic mean will become an unbiased estimator of the population mean capital X bar, which is indicated here as a X bar hat. Now, then we obtain one more sample from this sample that we have drawn in the first stage. So, now we have a sample of size n prime. From there I try to draw one more sample of size n by simple random sampling without replacement. Okay. And then suppose a small y bar and a small x bar, they are the sample means of steady variable and auxiliary variable based on this sample of size small n. Then obviously all the sample mean x bar prime, x bar and y bar, they are going to be unbiased estimator of their respective population mean, and then we had proposed the ratio estimator under the double sampling like this, y bar hat RD. So, this is the same thing, y bar upon x bar, and here it was earlier capital X bar, now it is replaced by its estimator, which is here x bar prime like this. So, and after this we had defined this epsilon 0, epsilon 1, epsilon 2 like this, and then we had found their means that was coming out to be 0, then expected value of epsilon 1 square was like this, then expected value of epsilon 1, epsilon 2 was the same as expected value of epsilon 2 square, expected value of epsilon 0, epsilon 2 was found like this, expected value of epsilon 0, epsilon 1 is this, and expected value of epsilon 2 square is here this, and expected value of epsilon 1, epsilon 2 here is like this one. So, this is what we have done in the last lecture. Now, I have just given you here a quick review, so that you are comfortable in using this expression in this lecture. Now, I am going to use the same technique that we had discussed in the case of ratio method of estimation. So, I will try to write down here with this here y bar hat RD is equal to y bar upon x bar into x bar prime. So, now I try to replace this y bar, x bar and this x bar prime as a function of different epsilons. So, small y bar becomes here 1 plus epsilon 0 times capital Y bar, small x bar becomes 1 plus epsilon 1 times capital X bar, and x bar prime, this becomes 1 plus epsilon 2 into capital X bar. This x bar get cancel out, and we get here this here y bar 1 plus epsilon 0, 1 plus epsilon 2, and this comes here 1 plus epsilon 1 whole inverse. So, I try to expand it using the Taylor series expansion, and where obviously that goes without saying that this expansion is valid only when absolute value of epsilon 1 is smaller than 1. And now we are going to use the same technique that we use in the case of ratio method of estimation, that you try to multiply all the terms and try to retain the terms up to the order 2, right, and all other terms wherever the terms have the powers more than 2, they are going to be ignored. So, you can see here the power is 1, here this power is 1, and here the power is here 2, with 1 here, and so this is going to be an approximate value of this expansion. And now this is here capital Y bar. So, this can come on the left hand side, and we can obtain the estimation error using this expression, right. So, we have ignored here all the terms which are of order more than 2. Okay. Now, in case if you try to find out here the expected value of here y bar hat RD. So, you can see here itself you can find out, you already have found the expected value of 0, epsilon 0, expected value of epsilon 2, expected value of epsilon 1, which are 0. And then you already have obtained the expected value of epsilon 0, epsilon 2, epsilon 0, epsilon 1, epsilon 1 square and epsilon 1, epsilon 2, right, that you can see here, right. So, now I simply try to substitute those values over here, right. So, these values become here 0, and I try to substitute here these 4 values. So, this is the value of epsilon, expected value of epsilon 0, epsilon 2, this is the value of expected value of epsilon 0, epsilon 1, this is the value of epsilon, expected value of epsilon 1, epsilon 2, and this is the value of here expected value of epsilon 1 square. Now, you see, you can very easily solve it. Just try to combine this and this together, and this together, right. So, this will come out to be, so you can see here this term get cancel out, and here also this term and this term get cancel out. So, you can obtain here this expression. So, this comes out to be y bar 1 upon n minus 1 upon n prime Cx minus rho Cy, where your Cx and Cy as usual, they are the Cx is the coefficient of variation of x, and Cy is the coefficient of variation of y. Right. So, obviously, now you can see here that that this small n and small n prime appear here, and you can see that here if your small n is large, then this means bias becomes very small, and this vanishes if this term is equal to 0. So, Cx minus rho Cy is equal to 0 means Cx is equal to rho Cy, or you can write down here, means on both the sides you try to multiply here by Cx. So, that is the same thing which you have written here, Cx square minus rho Cx Cy, if you try to write down here. So, right, then you can simplify it here, say Cx square equal to Cxy. And this condition, if you remember, we had earlier discussed also, this condition is going to be satisfied when the regression line of y on x is passing through the origin. And if you remember, that was also the condition for the superiority, or the for the condition when ratio estimator is going to give you a good result. Right. So, that was the condition that the regression line of y and x is passing through the origin, and we have seen that if it is not passing through the origin, then regression method is employed. So, you can see here now how is the change that has appeared in the expression for the bias of this expression when x bar is unknown to us, when capital X bar is unknown to us. And you can see here that there is a effect of the sample sizes n and n prime, which are obtained in the first and second phases. Okay. Now I try to find out the MSE. So, you know that in order to find out the MSE, what you have to do? You have considered here the estimation error, right. From here you can write down here y bar RD minus y bar, and then this will become here y bar epsilon 0 plus epsilon 2 minus epsilon 1 something, then you have to take here a square, right. So, you know that if there is a term here like epsilon 0 epsilon 2, and if you try to take its square, then its power is going to be more than 2. So, what we are trying to do here, that we are trying to report here only these three terms, epsilon 0, epsilon 2 and epsilon 1, for which we know that and are we trying to square it, their powers are not going to be more than 2. Okay. So, this is this is the approximate value of the square of the estimation error of this ratio estimator under the double sampling, and this has been obtained after ignoring all the terms which have got the orders or powers more than 2. So, if you try to expand it, this will come out to be this epsilon 0 square, epsilon 1 square, epsilon 2 square, epsilon 0 epsilon 2, epsilon 0 epsilon 1 and epsilon 1 epsilon 2, right. And if you see here, you already have proved here, means if you try to see here this result, I will try to use here a red pen, this thing, that expected value epsilon 1 epsilon 2 is equal to epsilon 2 square. So, I try to replace here epsilon 1 epsilon 2 by here epsilon 2 square, and now you see all these expectations you have obtained here, epsilon 0 epsilon 2, epsilon 0 epsilon 1 and epsilon 2 square. So, you simply have to just substitute these expressions over here, nothing more than that, right. So, okay. So, now this here epsilon 2 square minus 2 epsilon 2 square. So, that will become here minus epsilon 2 square, right. So, this is, I have simply written these expressions over here there from the result that we had obtained earlier. I think this is not difficult. Yeah, this is a little bit lengthy and time consuming that you have to write all the expressions without any mistake. And then if you try to see here, I am simply trying to take here the common. There are 3 factors here with 1 upon n minus 1 upon capital N, this and here this. So, if you try to take them common, then this is a Cx square, Cy square and minus 2 rho Cx Cy, which comes here, right. And these things and the remaining part is here. This 1 upon n prime minus 1 upon n comes from here, and this becomes a Cx square minus plus rho Cx Cy, right. So, here there is a minus sign here, you have to notice, and here there is a plus sign. So, now this is here, but now that is not my objective. My objective here is this: can you identify this term? What is this thing? If you try to recall, this was simply the mean square error of the ratio estimator when x bar is known, right. But now you have here one more term like this one. And yeah, the positivity or negativity of this term depends on this factor. Okay. But this is the term which is going to indicate the contribution of the units in the second phase of sampling, or I can say in very simple word, this is going to create the change because of not knowing the capital X bar precisely. Obviously, when you are trying to estimate it, then there is some random variation in the value of x bar prime is expected, and so there is going to be some change in the MSE of the ratio estimator under the double sampling when x bar is not known, right. Now, means now you can compare here. Now, this is here MSE of y bar hat RD, and this is here MSE of ratio estimator. So, now you can take the difference of these two MSEs, and I can say that this ratio estimator under the double sampling is preferable over the ratio method of estimation if this term, if this term here is greater than 0, or this can be simplified to rho greater than half Cx upon Cy. Now, do you remember this quantity in the ratio method of estimation? This was a condition when you were trying to compare the ratio method of estimation with respect to the sample mean, that if you want to estimate the population mean capital Y bar, and suppose you have two options to use simple random sampling, or I can say use the sample mean to estimate the population mean, or you try to use auxiliary information, then this was the condition that was trying to indicate that should you use simple random sampling or the simple arithmetic mean of the values based on y, or you should use the auxiliary information also. So, obviously, we are saying that in the ratio method of estimation the success of the estimator becomes actually that depends on how closely x and y are related. So, that depends on the correlation coefficient between x and y, and this is indicated here, right. Okay. Now, if you try to see here, I try to write down this whole factor here, I try to divide it into two parts, this expression here. You can see here there is one factor which is depending on small n, there is another factor which is depending on small n prime, and there is remaining factor here which is depending on capital N. right. So, I try to write down the factors which are containing the terms small n and is small n prime here like this, and yeah, there is going to be some term I can write down here, say here 1 upon n, say v star, but since actually my objective here is something else, so that is why I am not bothered about this term. Actually, I want to find out what are the optimal choices for this n prime. Obviously, when you are trying to suggest the double sampling to any experimenter, the experimenter will have the first question, please let me know what should be my sample sizes in the first and 2 phases. So, obviously, one option is that that we can find out the values of n and n prime based on the cost function. Okay. So, now suppose the cost function is given by C0 is equal to nc plus n prime c prime. So, where this c and c prime, they are the cost of collecting the units in the samples of size small n and small n prime. Yes, you can ask me here that why there is no overhead cost, because overhead cost is actually fixed. So, I have included that overhead cost here in the C0, including overhead cost. So, that should not create any problem. Right. Now, we have a condition that the cost is given to us and cost is fixed, and we have to find the optimum sample sizes n and n prime for the fixed cost. So, for this thing we can use the Lagrangian function method that we have used earlier also, if you remember. Okay. Now, the Lagrangian function can be defined as, say, phi is equal to this variance part and plus this condition where this lambda is a Lagrangian multiplier. Right. And now you know that you have to differentiate this Lagrangian function with respect to n and n prime. So, whenever you are trying to do it, if there is a term like v star upon n which is a function of n, that will become automatically 0, and that was the reason that in this MSE function I have not included this term over here. Right. You must not think that okay, I am ignoring it. No, I am not ignoring it. But since I know my objective and I know what I am going to do, that is why I am trying to avoid it, so that my algebra, my terms looks simpler to you all. So, okay. So, I try to partially differentiate this phi function with respect to n and n prime, put it them equal to 0, and this will give us these two equations, lambda c is equal to v upon n square and lambda c prime is equal to p prime upon n prime square. Right. So, from this equation I can write down here like this, lambda c n square is equal to capital V. So, n becomes square root of capital V upon lambda c, or means I can write down here square root of lambda n capital C is equal to square root of capital V capital C. So, this is coming from the first equation. So, similarly you can do the same exercise and using this second equation I can obtain a similar term. So, you can see here that means if we proceed logically also, you simply have to replace n, c, v and capital C by their primes like n prime, c prime, v prime, c prime, etc. So, now we have here these two equations and now we have to solve them. So, what I try to do here from this equation, I try to find out square root of lambda here like this. Okay. Now, using this value of square root of lambda in this place here, I can make it in red color. right, and here I can obtain here the optimum value of sample sizes. You can see here this is a pretty simple algebra. I have simply just substituted here these terms, right. So, this is the optimum value of small n, which is indicated here as n optimum, and similarly for the n prime, the optimum value of n prime comes out to be here like this, which is indicated here as n prime optimum. Now, these are the optimum sample sizes for the first and second phases. Now, in case if you ask me what will be the optimum variance, what is going to be the variance by using this n and n prime as optimal values of n and n prime, then I will say simply you have this expression of the MSE, simply try to substitute it here, and we try to substitute it here. After doing this, if you try to solve it, the mean squared error of ratio estimator under the double sampling turns out to be like this one. Next question is that in case if we try to compare this MSE under the ratio estimation with double sampling with the sample mean under the simple random sampling. That means if somebody asks me that okay, the person has two options, to use the auxiliary information or to not, because the capital X bar is completely unknown to us. So, when capital X bar is unknown to us, then an unbiased estimator or the population mean under the simple random sampling will simply be the arithmetic mean of the sample observation on y1, y2, yn. But in case if somebody wants to use the double sampling, then the person has to draw a sample of size small n prime and then estimate capital X bar and construct the ratio estimated under the double sampling. So, definitely I would like to compare the variance of arithmetic mean which is obtained by the simple random sampling and the MSE of the ratio estimator which has been obtained in the double sampling, right. So, in case if X is ignored and all the resources are used to estimate only the capital Y bar using the sample mean small y bar as is the arithmetic mean of all the observation, then the required sample size will be C0 upon C without an issue, right, because C0 is the total cost and you are trying to see here you are trying to obtain a sample size of small n and the cost per unit of is C. So, n becomes here C0 upon C, no issues. And in this case the variance of y bar becomes here Sy square upon C0 upon C. So, you can see here that how I have obtained this expression of variance under WOR. You see the variance under WOR for this y bar is given by 1 upon small n minus 1 over capital N times Sy square. Now, since you are using the ratio estimation with double sampling, so there you are assuming that the sample size is pretty large, so that you can use the estimation technique which is based on the assumption that capital N is large. So, same thing you have to also do here. So, you try to approximate this expression when this population size is large. So, when n is here large, then 1 upon n becomes very small and this is approximately Sy square upon n, and now I am trying to replace small n by here C0 upon C, and this is giving me here this expression. So, now can I try to find out the relative efficiency? So, for that I try to take the ratio of the variance of y bar under SRS and MSE of the ratio estimated under double sampling, and then we are going to use here the optimum, right. So, this ratio will come out to be here like this. So, based on that now you have to take a conclusion that H1 has to be used, right. Okay. So, now I come to the next aspect, that up to now we have considered the ratio method of estimation and we have employed the double sampling methodology. Now, the same thing can also be done in the case of regression method of estimation, because in the case of regression method of estimation we also have the same assumption that capital X bar is known to us. So, now if the capital X bar is unknown to us, then we can simply use the double sampling methodology and we can estimate capital X bar and replace it there to construct the estimator, right. So, now we consider the double sampling in regression method of estimation. So, when the population mean of auxiliary variable capital X bar is not known, then once again we are going to use the double sampling in the regression method of estimation, and for that we follow the same thing, that we try to obtain a large sample of size small n prime from the population of size capital N by simple random sampling WOR, and then we try to estimate the population mean capital X bar by the sample arithmetic mean. So, this X bar hat becomes here X bar prime, small x bar prime. That is the same thing what we have done up to now. I am simply just doing the same analysis here once again. Now, then from this sample we try to draw here one more subsample of size small n from this sample of size small n prime, and observations on both the variables x and y are obtained. Then we try to replace capital X bar by a small x bar prime, and this will help us in assuming as if capital X bar is now known to us. So, in this case also, since we are trying to obtain the samples by SRS WOR, so the expectation of all the sample means X bar prime, X bar and Y bar, they will all be an unbiased estimator of their respective population mean, no problem. Now, if you remember, your regression estimator was earlier given as say beta hat minus X bar minus say small x bar. So, this was your here Y bar hat reg. Yes, now if you try to recall that when we did the regression method of estimation, then we had considered two cases in the regression method. One was beta was known and beta was unknown. So, obviously, we had also discussed that the case when beta is unknown, then we are going to estimate it from the sample, and this is a more justifiable case in real life application. So, here in the case of double sampling, we are going to use this case where we assume the beta is unknown to us. So, that is why I have replaced here beta by beta hat. Now, capital X bar is unknown to us. So, what we try to do? We try to replace it by X bar prime, and this is what I have given here, and this is your here regression estimator under the double sampling methodology. And where, as we have discussed earlier also, this beta is going to be estimated by this quantity beta hat, which is Sxy upon Sx square, and Sxy you know that is summation I goes from 1 to small n xi minus x bar yi minus y bar, and this Sx square is summation I goes from 1 to n xi minus x bar whole square. Here this beta hat, this is an estimator of beta, which is based on the sample of size small n, and this capital Sxy and capital Sx square, they are based on the population values. Okay. So, now if you try to see, if I ask you to find out the expected value of here y bar here reg under the double sampling y bar reg d, then now this will become expected value of y bar plus expected value of beta hat x bar prime minus x bar. Now, you see this is random, this is random, this is random. So, this entire quantity is stochastic, and it is not so simple to find out directly the expectation. So, what we try to do here, then we try to use here the same methodology to approximate the bias and MSE using the epsilons. But before that, you have to see how many epsilons do you need here, one for y bar, one for x bar prime, one for small x bar, and one for here Sxy and one for Sx square, because they are related here in the beta hat. Okay, so now we try to define these epsilons exactly in the same way as we have done in the past, and since we have employed the simple random sampling without replacements, so we know that is that expected value of a small x bar Sxy Sx square, they are the unbiased estimator of their respective population parameter, right. So we try to define here one epsilon 1 for a small x bar, like as a small x bar minus capital X bar upon capital X bar, epsilon 2 for x bar prime. So this is x bar prime minus capital X bar upon capital X bar, then epsilon 3 which is a small Sxy minus capital Sxy divided by capital Sxy, and similarly here epsilon 4 which is a small Sx square minus capital Sx square divided by capital Sx square. And then based on that I can write down this small x bar prime, small Xy, small Sx square like this. So now in case if you try to take their expectation, obviously they are going to be 0. This we already have done. Now in this case if you try to see here, expected value of epsilon 3 will become expected value of Sxy minus capital Sxy upon capital Sxy, and since we have used here the SRS WOR, so this expected value of small Sxy is going to be capital Sxy, so this becomes here Sxy minus Sxy upon Sxy, which is 0, right, and same is true for the epsilon 4 also. Okay. Similarly, you can also show that here expected value of epsilon 4 is 0, because expected value of small x square is equal to capital S square in the case of SRS WOR. Okay, so now what we have to do, we have to use these definitions of epsilon 1, epsilon 2, epsilon 3, epsilon 4, and we have to substitute them in this regression estimator under the double sampling. So you can see here this beta hat is actually Sxy upon Sx square. So now I try to substitute here all these epsilons. Here I am not intentionally using any epsilon for defining a small y bar, because this is appearing here linearly, right. So now I try to write down these epsilons for small x's, Sxy, Sx square, x bar prime and x bar here like this. That is pretty simple now. And then you can see here that this becomes here capital X bar Sxy upon Sx square 1 plus epsilon 3, epsilon 2 minus epsilon 1 here, and 1 plus epsilon 4 raised to the power of minus 1. So now I can expand this expression using the condition that absolute value of epsilon 4 is smaller than 1, right. So I try to expand it here like this, 1 minus epsilon 4 plus epsilon 4 square. Now actually you know what you have to do, you have to do. So but before that, if you observe this thing, what is this quantity? This is here beta. So now this expression becomes here y bar plus x bar times beta 1 plus epsilon 3, epsilon 2 minus epsilon 1, and then 1 minus epsilon 4 plus epsilon 4 square, and now I have to multiply these three quantities together, and we need to retain all the terms which have the powers up to order 2. Yeah, and we are assuming that absolute value of epsilon 4 is smaller than 1. And what is the interpretation, what are the consequences, that we know, that we had discussed in the case of ratio method of estimation. So I am not going to repeat it here. Now you try to ignore here all the terms which have power more than 2, and then we have this here finally this expression, and this is the approximate estimation error of regression estimator under the double sampling. Now you know that you have to simply take its expectation, you will get the bias, you square it, you will get the mean square error after taking the expectation, exactly in the same way as we have done just in the case of ratio method of estimation also, and in the double sampling case also. So, we simply try to take the expectation on both the sides. Expected value of y bar reg d hat, this will become expected value of here y bar, which is here capital Y bar. Then now x bar beta, and you can see here that all these terms epsilon 2, epsilon 1, they will become here, their expectation will become 0, and then you have here only these terms. So, this is what I am writing here, the expectation of these 4 terms. Now, you already have found these expectations, where if you see in the beginning itself you have found these expectations, right. And that is why if you try to see, we have I have used the definition for this epsilon 1 and epsilon 2 be the same, so that I do not have to compute these expectations once again. So, now I simply try to replace here these expectation, but there is one thing. Suppose if you try to see here what is this expected value of epsilon 2 epsilon 3, what is this all about? Epsilon 2 is about x bar prime, and epsilon 3 is about sxy, right. So, now finding out this expectation, that expected value of x bar prime minus x bar into sxy minus sxy, right, beside some other factors. This is not so straightforward. But if you try to write down this thing in the basic framework here, that this is going to be 1 upon n summation I goes from 1 to capital N, say x bar here minus capital X bar into sxy minus capital sxy, right. So, then this is the basic definition here, where all this sxy i's are appearing here, right. So, that is what I am writing here symbolically. This is the basic definition of such an expectation, expected value of this thing x bar minus time minus x bar into sxy minus sxy, right. And the same thing I try to do here with this expected value of epsilon 2 epsilon 4 here, like this, right. And then means obviously this term 1 upon n prime minus 1 upon capital unwind curve, because you are trying to find out the covariance between the two quantities, and where the samples have been drawn by the simple random sampling. And similarly, we try to write down the expectation value of epsilon 1 epsilon 3 and expected value of epsilon 1 epsilon 4. Now, you see it is difficult to find out these expectations. So, we try to indicate them symbolically using the definition of cross product movement that we have done in the case of regression method of estimation earlier also, where we had defined the mu r s is equal to expected value of x bar minus say x bar times here say here r, or y bar minus here y bar times here s, and so on, right. This would be here y. So, this type of thing. So, now you simply have to count that how many x and how many y's are appearing in a particular product. For example, if you try to look here in this expression, there are 2 x's and 1 y's, and if you come here, then there are here 3 x's, one x related to sample mean, and say another say related to x square. So, these things I am simply trying to replace it by here, say mu 2 1, mu 3 0, mu 2 1 and mu 3 0, where your mu 2 1 is given by this and mu 3 0 is given by this. And after that, you simply have to just simplify it, and you will get here this term, which is the bias of the expected value of the regression estimator under the double sampling. And then if you want to find out the mean square error, what you have to do? You simply have to just write down this expression, that expected value of y bar reg d minus capital Y bar whole square, and then you try to write down this here reg d, and then try to combine this small y bar and y bar here together, and then try to write down all those expression in terms of epsilons as we have done in this earlier case. And now you try to expand it and try to retain all the terms up to the second order of approximation. So, that is what I am trying to do it here. So, here I am writing the exact expression, and then this is square, then I try to expand it and I try to retain all the terms up to the order, say here 2, and here we are also assuming that absolute value of epsilon 4 is less than 1. So, under this thing, this expectation will come here, right. So, now you have here all this expression. What is this thing? This is simply your here variance of y bar, and now you already have obtained the expected value of all these squares, right. So, now you simply try to substitute it and get them simplified. So, once again I am simply trying to replace here all the things, all this expectation that I have obtained earlier, and if you simply try to simplify it, this will come out to be like this, and if you take the combine these two factors, this will be here like this, right. Yeah, pretty simple, then not difficult. Then you try to substitute here the value of beta here, and then you try to simplify, this will get cancel out, right. And then you have here finally this expression, right. And then here this quantity here, this Sxy, I am trying to write down here rho Sx Sy whole square. So, this becomes a square and Sx square. So, this gets cancelled out, and we have here rho square Sy square. So, now this is the term of this MSE of regression estimated under the double sampling. So, now you can write here the terms involving 1 upon n and say 1 upon here n prime, and then the term related to the 1 upon capital N, I am just trying to ignore it, right, and then I am trying to approximate it, because I want to do the same algebra which I did in the case of ratio estimation in the double sampling, but I would like to find out the optimum value of this small n small n prime. Now, what I try to do here, and then means also I can say assume if the population size is large, and how the things are going to happen. Okay. So, anyway, I try to write down this expression over here. So, this is the expression. So, now you can see here, it is clear from here that what is here, this is Sy square upon n, which is the variance of sample mean under the SRS when no other auxiliary information is used. So, clearly this quantity, this MSE of y bar hat reg under the double sampling is more efficient than the sample mean under the SRS, and that is obvious also, it is using more information. Now, we try to do the same thing that way that we did in the case of ratio method of estimation, and we try to find out the optimum sample sizes of n prime, and that is going to address the issue whether the reduction in the variability is worth the extra expenditure required to observe the auxiliary variable, because that is what we discussed, that you have to devote some of your funds for drawing one more sample to estimate your capital X bar. So, once again I take the same setup, that the cost function of this survey is given by C0 is equal to C1 n plus C2 n prime, and where the C1 and C2 are the cost per unit observing the auxiliary variable y and steady variable y and auxiliary variable x. Okay, now I try to use the Lagrangian multiplier method. I try to write down this function over here like this, then I try to differentiate it with respect to n prime, put it equal to 0, get these two equations, exactly the same methodology which I have just repeated, right, and then try to solve this equation. This will give you here n equal to square root of Sy square 1 minus rho square upon lambda C1, and from here you can get here n prime equal to rho Sy divided by square root of lambda times C2. Right. So, now you have obtained the n, but this involves here lambda. So, now in order to find out this lambda, I try to substitute this value of n prime in the cost function like here like this, and I simply try to solve this equation, and this will give us the lambda value here to be here like this. Now, I try to substitute this lambda value here and here, and then I try to obtain the optimum sample size of n prime and n here like this. So, here you see, yeah, algebra is little bit lengthy, but not complicated, and unless and until you try to do the simple algebra with your own hand, it might be a little bit difficult, and it will be very helpful if you try to do it yourself, right. And then in case if you want to find out the optimum mean square error of this regression estimator, then just substitute n equal to n optimum and n prime equal to n prime optimum in the MSE what you have just obtained here, right, this expression what you have obtained, right. You just try to substitute it here, and you will get here this term, and if you simply try to solve here, you will get here this term, right. It is not difficult at all. Now, in case if you want to compare it with the sample mean, as we have done in the case of ratio method of estimation. So, I had shown you there that n is going to be here C0 upon C1, the same setup, right. So, the variance of SRS that we have just obtained, that is equal to, that is here like this. If you try to see here where I had obtained, I can show you, this is, you see, this is what we had obtained the variance of y bar. Now, I am simply trying to use it. It's simply a repetition of the same thing. Okay. Now, I try to find out the relative efficiency by taking the ratio of the variance of y bar under SRS and the mean square error of this regression estimator under the double sampling and its optimum value, and this ratio this value comes out to be like here this, which can be simplified to be here like this, and since rho square is always greater than 1, right. So, this term relative efficiency comes out to be always less than equal to 1. So, now what I can say that this double sampling in the regression estimator will lead to gain in precision if C1 upon C2 is greater than rho square upon square of 1 minus square root of 1 minus rho square. That is the condition, right. Okay. So, now we stop in this lecture, and now you have seen that we have now done both the cases, that if somebody wants to apply the ratio or regression method of estimation, then there is a condition that capital X bar should be known to us. So, if X bar is known to us, no issues, you try to use the ratio and regression method of estimation, and if X bar is not known to us, then you try to use this double sampling, estimate capital X bar from the population itself by taking a sample of large size and then replace it there. Yes, the algebra is a little bit going to be lengthier, but again I will say lengthier does not mean difficult. So, my request and my suggestion to you all is that you try to do this algebra with your own hand, own pen and own paper, and I am sure that there should not be any problem, any confusion in understanding these concepts, in finding out this bias, MSE, etc. They are the same stereotype of things now. Define epsilons, write down estimation error, take its expectation, square the estimation error, take its expectation and try to approximate it. This is the basic methodology. But you must understand that why you are doing this methodology and how are you going to implement it using the condition. For example, whenever you are trying to expand any term, the corresponding epsilon value, the absolute value of that epsilon should be less than 1. That means that variable, the corresponding variable is lying between 0 and twice of the population value. For example, small x bar will be lying between 0 and twice of capital X bar. Small sx square will be lying between 0 and twice of capital Sx bar. That we have to discuss in the case of ratio method of estimation when I introduce this estimation technique for the first time. So, all those concepts will continue here. So, I will say, I will request you, I will suggest you that you try to have a look, try to practice and try to revise this lecture, and I will see you in the next lecture. Till then, goodbye.